Next, we are going to see the ASM chart. So this is a topic of third unit, ASM chart. So the three basic elements of ASM chart are state box, decision box, and conditional box. So these are the three basic elements of ASM chart. Before going into the basic elements, we must know what is the ASM. ASM is nothing but algorithmic state machine. So the function of the state machine can be represented by state table or state diagram. A flowchart is a way of showing actions and control flow in an algorithm. What is flowchart? It is a way of showing actions and control flow in an algorithm. But an algorithmic state machine is simply a flowchart like way to specify state diagram for sequential logic and optionally actions performed in the data path. So the algorithmic state machine is a flow chart. It is a way to specify state diagrams for sequential logic and optionally actions performed in the data path. So flowchart typically do not specify time, but ASM explicitly specifies a sequence of actions and their timing relationship. So the ASM chart will specify the sequence of actions and their timing relationships. Now, the same flowchart is a convenient way to specify the sequence of procedural steps and decision path. And ASM chart provides not only the sequence of events but its timing relationship. Now, the elements of ASM chart. Already I have told you that it is having three elements. One is state box, second one decision box, and the third one conditional box. These three are the elements of ASM chart. This is state box, and the second one decision box, and the third one conditional box. Now we will see these three elements in detail. So state box represent a state. This is state box. State box is in rectangle shape and it represents a state equivalent to a node in the state diagram or a row in the state table. So the state box is equivalent to a node in the state diagram or a row in a state table. So it contains register transfer actions or output signals. So the state box will be having register transfer actions and output signals. So more type output are listed inside the state box. So if it is a more type of circuit, then the output is mentioned inside the state box. Next is a decision box. So a decision box is diamond in shape and it indicates that a given condition is to be tested and the exit path is to be chosen accordingly. The condition expression may include one or more inputs to the FSM. Okay, so this is decision box. It will verify the condition expression and it will be having either true or false. It indicates that a given condition is to be tested. If there is a condition, that condition is to be tested either true or false. So this is decision box. And next one is conditional output box. Conditional output box denote the output signals that are of melee type. So in more type we will be writing the outputs inside the state box, but in melee output will be writing in the conditional box. The condition that determines whether such outputs are generated is specified in the decision box. So here the the condition that determines whether such outputs are generated is specified in the decision box. This conditional box will be telling. Okay, it denotes the output signals of the melee machine. You know, this is a ASM block. An ASM block will be having one state box, one or more decision box, and one conditional output, one or more conditional output box. So what is an ASM block? ASM block is nothing but it will be having one state box. It must have one state box, but it can have one or more decision box and one or more conditional box. Then ASM chart rules. Difference between a regular flowchart and ASM chart is ASM chart transition is governed by clock. Transition occurs between ASM blocks in ASM chart. Basic rules. For a given input combination, there is one unique exit path from the current ASM block. Okay. So, for a given input combination, there is only one unique exit path for a current ASM block. A closed loop in a ASM chart must include a state box. So, a closed loop must include a state box. Now, these are the incorrect ASM. Incorrect ASM means the state box must have only one conditional box. Here you are having two conditional. It is also wrong. Similarly, a loop must have a state box. The second one, any closed loop in ASM chart must include a state box. So here the loop we are taking it to the conditional box, so it is wrong. Similarly, here the first one, for a given input condition, there is a unique exit path from the current ASM block. So there will be only one unique exit path for this state box. Okay, these are the incorrect ASMs. So here this it has to go to the state box and not to the conditional box. And here there must be only one conditional box and there should not be two conditional box. Next, this is a correct ASM chart. So this is a state box, then you are having a conditional box, then this feedback you are going to a state box, then this is being you are going to an conditional box, then you are having an conditional output box, then you are going to a state box, then you are going to a feedback. Okay, so this is a correct ASM chart. So next we are going for a problem. So we are going to detect a sequence 1 0 using a sequence detector. So this is a state diagram of Moore machine. In Moore machine, we will be writing the output inside the circle, and in Mealy, you will be writing the output in the transition edges. So we are in state 0, or we are in state 0, and we are receiving the first input as 0. So here the sequence is 1 0. We have to detect the sequence 1 0. Since we are detecting the 0, we are in the present state. Next we are detecting 1. So it is going to the next state B. So in the next state B, again you are detecting 1. So it is in the present state B. The output is 0. Here also the output is 0. Now then you are detecting a 0. So you are going to C. Since we have detected the entire sequence 1 0, here the output is changing to 1. So once again I am telling this problem is nothing but detecting a sequence 1 0. Okay, so you are in state A and you are considering the state A is having 0. Now we are getting an input of 0. So it means that we are not recognized the first bit of the sequence. So it will be in the same state A. The output is 0. Similarly, it is recognizing the first one. It is getting an input of 1. So it has recognized the first bit. So it is going to the next state B. It is going to the next state B. It is going to the next state. It is going to the next state P, and output is 0. Why? Because we have not recognized the entire sequence. Next it is receiving a 1. So next we have to recognize a 0, but we have recognized a 1. So it is in the same state B. Then we are getting a 0. So it is going to state C. And since we have recognized the entire sequence, the output is changed to 1. From this, we are getting a 1. From C, we are getting a 1. It is coming to B. When we are getting again a 0, when you are getting again a 0, it is coming to the initial state. So this is nothing but a state diagram of an uh, um, sequence detector which detects the sequence 1 0. So this is a Moore circuit of your sequence detector. Now this is a ASM chart for Moore FSM. So you are in a state A and first input what you are receiving is 0. So actually we have to recognize 1 0, but we have recognized 0. So we are going to the first state in the present state A. Then you are going for a if you are getting 0, you will be getting the same state. If you are getting 1, you are going to the next state B. Then from B, then you are checking whether 1 or 0. If it is 1, you are in the same state because the next number what you have to detect is 0. If you are getting a 0, then you are changing the output to 1. Then you are changing the output to 1. Again, you are detecting. If it is 1, you are coming to the B. If you have 1, you are coming to the state B because there is a chance for again a 0 will come, the next sequence will start. If it is 0, you have to come to the initial state. This is the ASM chart for Moore. Now we will see the ASM chart for Mealy. Now you are in state A. If you are receiving a input 0, you are in the same state, then output is 0. If you are receiving a 1, you are going to state B. You are going to state B, but the output is 0 only. In B, you are recognizing a 1, you are in the same state. But again, if you are recognizing a 0, you are changing the output to 1 and you are coming to A. So this is the Mealy's state diagram for Mealy. Now we are going for the ASM chart for Mealy. Now you are in state A, you are checking the input. If it is 0, you are in the same state. So if it is 1, you are going to the next state. From the next state, again you are checking. If your input is 1, you are coming to the previous state. If you are 0, you are coming to the initial state A. You are writing the output in the conditional box. But in the case of ASM chart using Moore, you are writing the output in the state box. This is the difference between the ASM chart for Mealy and Moore. Now this is a mod 6 counter. This is a state diagram of mod 6 counter. So mod 6 counter will count from 0 to 5. If 0 is a present state, if it is getting an input of 1, it will go to 1. If it is getting an input of 1, then again it will go to the next state 2, then 3, then 4, then 5, etc. If it is getting a 0, it will stay at the present state. So this is the state diagram of a mode um, 6 counter. Mode 6 counter means it will count from 0 to 5. Okay, it will count from 0 to 5. It will getting a, if it is getting an input of 0, it will stays at the present state, and if it is getting an input of 1, it will goes to the next state. After completing the entire sequence, the output will be changing to 0. Till then the output is 0. After output is changing to 1, it will come to the initial state. Now this is the ASM chart for mode 6 counter. First you are in state 0 0 0. You are checking the input. If it is 1, you are going to 0. If it is you are going to the next state 1. If the condition is 0, you are coming to the same state. Similarly for the next one, you are in state 1. If it is 1, you are going to the next state 2. If not, you are coming to the same state. Similarly, after completing the full state up to 0 to 5, you are then checking x is equal to 0, then you are coming to the same state. If x is equal to 1, you are making the output as 1 and you are returning to the initial state. So this is nothing but the state ASM chart for mode 6 counter. So here you are having an input. The input is 1, you will be going to the next state. You are having one state box and one conditional box. Finally, after completing all the states, you are using the conditional box to represent the output. Okay, in all other cases you are having one state box and one conditional box. If condition is 1, you go to the next state. If conditional is 0, you go to the previous state. So this is nothing but mod 6 counter by using ASM chart. Next, we are going to see binary multiplier. So, we are going to see the ASM chart for binary multiplier. So, how multiplication is done? Actually, multiplication is done by shifting and adding operation. So, here, this is the first partial product, second partial product, third partial product, and fourth partial product. Here we are adding. So, here you are shifting each partial product, you are shifting and then you are adding. So in multiplication, what actually you are doing is shifting and adding. Okay, now this is a data path system for binary multiplier. So this is a multiplicand, b0 to bn is a multiplicand and q0 to qn is a multiplier, and you're having shift and add control, and here you are having an adder. So actually in multiplication you are just shifting and adding. So this is a C bit register, it is a 1 bit register. Okay. So A is a accumulator or A register. So now you will see it very clearly. So the multiplication operation is here. If the bit 0 of multiplier is multiplier operand, you are checking. First bit, the bit 0 of multiplier operand, you are checking. If bit 0 is 1, so if bit 0, first we are checking the bit 0 of multiplicand. If it is 1, then multiplicand and partial products are added, and all bits C, A, Q are shifted right by 1 bit. So if the first the bit 0 of Q naught, that is multiplier, is 1, then what you are doing is you are adding the partial product with the multiplicand, and you are shifting all register by 1 bit. If it is 0, if the bit is 0, then no addition is performed, only shifting operation. So the bit 0 of q naught is checked. If it is 1, you are adding that multiplicand with the partial product, and you are shifting the register C, A and Q by right 1 bit. And if it is 0, then only addition is no addition is performed, only shift operation is carried. Okay, so the steps 1 and 2 is repeated n times to get the desired result. We will see it clearly. Okay, so now flow chart for the multiplication. First we are starting, then we are making the registers C and A0. Then you are loading the multiplier in the B register, and you are loading the multiplier in Q register, and you are making the count as N. N is nothing but the number of bits. Okay, the multiplier and multiplicand. Now you are checking the first bit of Q naught. If it is 1, then what you are doing is you are adding A and B. You are adding A and B. Then if it is 0, so after adding you are shifting the registers. Okay, then after shifting the register you are making the count as n minus 1. If you are having n, you are making it as n minus 1. You are decreasing the count. If it is 0, if q naught is not 1, then you are just only shifting. So if the first bit is 1, you are adding with the multiplicand, and partial products with the multiplicand, and you are shifting. If it is 0, you are only shifting, and you are continuing this operation up to n becomes 0. Okay, now we'll clearly we will check here. First we are storing B. So here this is B. B is a multiplicand and Q is a multiplier. So B is a multiplicand and Q is a multiplier. So we are checking the first bit of the multiplicand. So here it is 0. So no addition is performed. We have to only shift this right by 1 bit. Okay. So here you are shifting this by 1 bit. So this 0 will come out. This 1 will come in. then 0, this 1, then this 0 will come here, then here having 0. So if this first bit is 0, then what you are doing is you are only shifting it right by one bit. This whole Q, A, Q, A and C. That is, initially you are having this one. This 0 will be coming out. Then 1, 0, 1, this 0. Then you are having 3 zeros. Then this C0 will be coming here. Then again the C is 0. So this is the first step. Okay. Next, you are making the count. Here it is 4. You are changing it to 3. Next, again you are checking the next bit. Here it is 1. So what you have to do is you have to add the multiplicand with the partial product. Okay. So here you are checking 1. So you have to uh, multiplicand, right? You have to add this multiplicand with this partial product. This is the partial product. Okay. So 1 plus 1101 plus 000 you'll be getting 1100. So after that you have to shift it by one bit. So what you have to do, you have to shift it by one bit. So this 1 will go out, so you'll be getting 0 1 0. This 1 will be coming here, you'll be adding 0 1 1, and this 0 will be coming here and 0. So next what you're doing is you're shifting it by one bit. So you're getting like this. So after shifting, you have to change this count to 2, decrease the count. So 3 will become 2. Again, the first bit is 0. So you have to only shift it by one bit. You are shifting it by one bit and you are reducing the count to 1. Again, the first bit is 1. So what you have to do is you have to add this 1101 with this partial product 0011. So 1101 plus 0011. So 1 plus 1 is 10, 1 plus 1 is 10, 1 plus 1 is 10, 1 plus 1 is 10. So here you are getting 000 and a carry. This carry you have to put in the place of C. So I will clearly tell. So while adding these two, you'll be getting this one. This is the carry and you're getting 000 here. Okay. You have to write the same thing here. Then what you have to do is again you have to shift it right by one bit. So this one will go out. So 010. Then this 0 will be coming here. Next you are having only 3 zeros and this one will come here. Okay. This one will come here. So this is your answer. So this is nothing but this number. Actually, this is 13. This is um, so this is 13 and this is 10. When you multiply 13 into 10, you'll be getting 130. Okay, this is a binary equivalent of 130. So 1000010 is a binary equivalent of 13. Okay, once again I will. So we are loading the multiplicand in the P and we are making C as 0, A as 0 and multiplier in Q and we are making P as a count 4. Then first we are looking the first bit of multiplier. If it is 0, no addition is required, just we have to shift it right by one bit. So here we have shifted right by one bit and we are reducing this P to 3. Then we are again checking the first bit of multiplier. It is 1. So we have to add this partial product A with B. So we have added this partial product A with B and then we have to shift this Q, A and C right by 1 bit. So here also you have to shift Q, A and C by 1 bit. Then we are shifting it right by 1 bit. So we are getting this, and we are making the count P as 2. Then we are again checking this first bit. This value is 0. So no addition is required. Just we are shifting Q, A and C right by 1 bit. Again the value is 1 here. So addition is required. So we have to add this partial product with this. So here you are having 1 1 0 1 and you are having 0 0 1 1. While adding you will be getting 1 0 0 0 0. So that one you have to write in the C register. So you're getting, and you have to shift it right by 1 bit. So you are getting this. So the answer is, this is 13. Actually B is 13 and A is 10. While multiplying you will be getting 130. So this is the binary equivalent of 130. So this is a binary multiplier. Now this is a ASM chart for binary multiplier. You are in initial state 0 0 and you are checking the condition S is equal to 0 or 1. If it is 0 you are going to the initial state. If it is 1 you are going to the next state 0 1. In that state what you are doing is you are making A is equal to 0, C is equal to 0 and making P as count N. Then you are going to the next state 1 0. In the next state what you are doing is you are decreasing the count value to 1. Then you are checking the first condition. If q naught is 1, you are going to add a plus b, and you are adding a plus b and you are making c out as c. Okay, then you are going to the next state. So if it is 0, no addition is required. Directly you are coming to shift. You are going to shift C, A and Q. If it is 1, after adding you are coming to the shift stage. You are shifting CAQ right by 1 bit. Okay. Then you are checking the condition Z. If it is 1, it is going to the initial state. If it is 0, it is going to the count. Okay, again you are going to the count state. If it is 1, it is going to the initial state, and if it is not 0, it is if it is 0, it is going to the count state. So this is a ASM chart for binary multiplier. Okay, so here actually what you are having is initial. You are having you are in an initial state, and you are checking a condition. If it is 0, you are going to the initial state. If it is 1, you are going to make the A register, C register and P register. A register and C register 0 and P register as 1. Then you are going to the next state. In the next state what you are doing is you are reducing the count. You are reducing the count there. Then you are checking the Q naught bit. If it is 1, you are going for adding, then shifting. You are adding and you are shifting. Next, if you are if it is 0, Q naught bit is 0, just you are shifting. Okay. Then if the count is 0, you are stopping there. If the count is 1, then if the z is a conditional value. If it is 0, you are going to the S2 state. If it is 1, you are going to the initial state. Okay, this is a ASM chart for binary multiplier.